Welcome to the Explainer. I am so incredibly pumped you're hanging out with us today because, honestly, we've got a fantastic tech underdog story to get into. We're talking about how machines actually understand human language. Now, you might think modern AI is all about these massive, incomprehensibly complex neural networks, right? Well, today we're zooming in on a classic, old-school technique that just absolutely refuses to step down.
Okay, let's dive into this. The dumbest one that works. In software engineering, that's practically the highest compliment you can get. It perfectly describes this classic counting method we're looking at today. And the crazy part, it still beats out massive 400 million parameter AI embedding models right now in 2026 for specific, well-defined tasks. Let's unpack exactly why that is.
But first, we really have to look at the foundational problem of literally every single natural language processing pipeline out there. It's all about translation. See, machine learning classifiers need numbers. They just want to do math. But human language gives us this messy, variable-length stream of words. So the big question is, how do we turn those unpredictable words into a fixed-size mathematical format?
So here's our roadmap for the explainer. Number 1, the core problem. Number 2, the mechanics of bag of words. Number 3, the TF-IDF upgrade. Number 4, where this underdog actually wins out. And finally, number 5, its semantic blind spots. Let's get right to it.
Section 1, the core problem. Because really, before a machine can even begin to analyze our text, whether that's a quick tweet or a long email, it absolutely has to translate that text into something it can mathematically digest.
And the very first major answer the NLP world came up with is the bag of words model. Now, what does it do? Well, by definition, it just ruthlessly throws away order. It completely tosses out grammar, syntax, the whole shebang. Instead, for every single document, you literally just count how many times each vocabulary word shows up. That's it. The length of your final mathematical vector is just the size of your total vocabulary, and each spot in that vector is simply the count for that specific word.
Count the words, make a vector. It sounds almost too simple, doesn't it? Like, there's no way that actually works. But actually, this incredibly straightforward mechanism has carried more production NLP than literally any modern embedding model out there. We're talking early spam filters, topic classifiers, log anomaly detection, search ranking before BM25, and the very first wave of sentiment analysis. All of it was built on this simple counting trick.
Section 2, the mechanics of bag of words. Let's move on and actually see how this builds step by step from scratch.
The technical execution breaks down into 5 really clean steps. Step 1, you build your vocabulary, basically a dictionary mapping every unique word to a specific index number. Step 2, you create your bag of words. Your rows are your documents, and your columns are those vocabulary indices. So if document 1 has the word cat in it twice, boom, you just drop a 2 in that column. Steps 3 and 4 involve reweighting those counts, which, hold that thought, we'll get to in just a sec. And finally, step 5, L2 normalize the rows. This is absolutely crucial. Without it, a really long document gets a massive vector and just completely wrecks your similarity scores. L2 normalization smoothly puts every single document onto a unit hypersphere, which is just a fancy way of saying it lets you compare them fairly using simple math.
Section 3, the TF-IDF upgrade. So raw counting is great, but it has a major flaw. It treats super ubiquitous, totally boring words exactly the same as rare, highly informative words. We definitely need an upgrade.
So the crucial point here is understanding the difference between term frequency and document frequency. Term frequency is super simple, just the count of a word in one specific document. But document frequency zooms out. It asks how many total documents contain this word. Think about it, if a word appears in literally every document, it tells us absolutely nothing unique. So we apply something called inverse document frequency, or IDF. It uses a logarithm to scale that common word's weight way down. On the flip side, if a word is super rare across your whole dataset but shows up a bunch in one specific document, that is pure signal, and IDF scales its weight right up.
And honestly, the beautiful part about all of this is that you don't even have to code the math yourself. Scikit-learn ships the production version of this right out of the box, with some amazing little knobs that change everything. For instance, you can boost classification by grabbing 2-word phrases using the n_range argument. You can easily trim out noisy data with min_df, or, this is cool, elegantly drop all your stop words just by setting max_df to 0.95. No clunky hard-coded list required. Oh, and flipping on sublinear_tf does wonders for beautifully taming those annoying repeating terms.
Section 4, where the underdog wins.
So with all the crazy AI tech out there today, why do top-tier practitioners in 2026 still reach for this exact counting method first when they have a narrow task?
And this brilliantly illustrates the primary reason: microseconds. Look, shoving a document through a modern transformer model takes anywhere from 10 to 100 milliseconds. It's sluggish. But TF-IDF, paired with a simple linear model, it spits out an answer in microseconds. When you have strict latency constraints, that raw speed is just flat out unbeatable.
Let's rapidly rattle off some of the other undeniable benefits here. First, it absolutely dominates on word presence tasks. Think spam detection or spotting log anomalies, where you really don't care about deep semantic nuance, you just need to know if specific trigger words are there. Second, low data regimes. If you only have, say, a few hundred labeled examples, TF-IDF is your best friend because it has exactly zero pre-training cost. And finally, absolute explainability. Try looking inside a 768-dimensional BERT embedding. It's a total black box. But with TF-IDF, you can literally just look at the coefficients and read exactly which specific words caused the model to make its prediction. It's amazing.
Section 5. Semantic blind spots. Of course, no method is perfect. We have to acknowledge the kryptonite of our underdog. Where does this count first, think later methodology completely fall apart?
Now, what's really interesting about this is the concept of complete semantic blindness. Take a look at these two sentences. The movie was not good at all, and the movie was excellent. Obviously, one is super negative and the other is glowing. But check out their TF-IDF overlap. It's the exact same set of words, the, movie, and was. Because it doesn't understand context, a bag of words classifier has to rely purely on brute force memorization. It basically has to learn that if the word not happens to appear anywhere near the word good, it probably needs to flip the label. It is never going to handle this as smoothly as a model that actually understands real syntax.
And then there's the second major flaw: out of vocabulary failure at inference. Let's say you train a bag of words model on a bunch of old IMDb classic movie reviews. If you suddenly feed it new, modern Zoomer slang, it's going to flat out crash, or at least fail silently. Why? Because that specific new token was never in the original training dictionary. It can't intuitively guess the meaning of a new word based on its subparts like a modern model can. It literally only knows how to count exact matches.
So what's the pragmatic compromise for us right now working with medium-sized data? Well, it's this really clever hybrid approach: TF-IDF weighted embeddings. It's exactly what it sounds like. You use your TF-IDF weights as an attention mechanism over your modern word embeddings. You pull those vectors together, and you get the best of both worlds. You get the deep, contextual, semantic understanding of modern embeddings, but you also keep that laser-focused, rare word emphasis that TF-IDF is so good at. If you've got under 50,000 labeled examples, this hybrid approach will consistently outperform either method entirely on its own. It's a real game changer.
So what does this all mean? It leaves us with a pretty fascinating question. In an era where everyone is completely obsessed with billions of parameters, massive compute costs, and complex syntax trees, could the absolute simplest counting math still be the secret ingredient in your next AI pipeline? Honestly, sometimes the dumbest one that works isn't dumb at all. It's just a masterpiece of efficiency. Thanks so much for joining me on The Explainer today, and hey, always keep an eye out for the simple solutions hiding behind complex systems.